Let's say Jeanette and her godsister Erica want to make fruit baskets for their friends and family. But not just any fruit baskets. They want to pick sets of fruits that have a strong meaning when they're put together. A relationship with shared commonalities and differences. A purpose. Fruit with a story. But what exactly that story is, that's beyond them right now. So with no plan in mind, they decide to go to the farmer's market. And for 5 minutes grab whatever fruit they each like separately and throw it in their cart. When the 5 minutes are up, they both peep into their carts to see sets of fruit that can definitely tell a perfect story for their first fruit basket. There's some overlap between what they've chosen, some fruits that seem to be from the same category, and others that seem to stand out. In fact, Jeanette and Erica's fruit basket has many stories to tell. And whenever we want to explore categories or home in on information in order to build new, precise ideas, we can turn to the language of math and set theory. This time, we'll slice and dice our fruit with set operations to reveal all sorts of interesting relationships. I'm Jason Guglielmo, and this is Study Hall Real World College Math. Remember from our last 2 episodes that a set is a well-defined collection of objects, which means we can definitively decide whether something is or isn't in our set. Now, whatever set we're working with exists within a wider world, whether it contains numbers or fruits or the cousins in your family. For instance, say we have a set that contains you and your favorite cousin, but your family overall could contain a lot more cousins, even if they're kind of annoying. And sometimes in order to learn more about our set, we need to talk about that wider world. So we call the world our set lives in, and all the possible elements it could contain, the universal set. In the case of our set of cousins, our universal set contains all your possible cousins within your extended family. There's lots we can do within the world of a universal set and all the possible elements it contains. But we're going to take the scenic route while explaining today's episode, because we don't just want to explain what the rules are, we want to explain why they exist and where they come from. So, let's get started. First, remember that sets aren't just containers for stuff. They're also mathematical objects that we can manipulate the same way we can manipulate other math things, like numbers. In fact, let's step away from fruit and cousins and talk about numbers for a moment. Take the numbers 7 and 9. One of the worlds or universal sets they live in is called the set of real numbers, which are all the numbers that can either be written as fractions or with infinite decimals that don't repeat. Basically, numbers we deal with every day, like 7, or square root of 2, or 10,090 seconds. Now, let's say we wanted to manipulate the numbers 7 and 9, like by smashing them together. Now we have 16, and you probably recognize that this smashing together rule has a name: addition. There are other rules we can use to manipulate real numbers too, like subtraction, division, or working with exponents. Each of these rules, or operations, tells us how 2 elements from the same universal set are related to another element within the same set, and we call each rule a binary operation. Binary operations are usually represented by a symbol. Like when we see a plus sign, we know that's standing for addition. Or we can think about the binary operation multiplication, which has a lot of different symbols, like using a little x between 7 and 9, or writing 7 in parentheses and 9 in parentheses and sitting them next to each other. No matter how we write it though, the way we've decided multiplication works with the set of real numbers means that every time we multiply 7 and 9, we'll get 63. But it's important that we're clear on what universal set we're working with. If we tried to add or multiply the number 7 and the color blue, well yeah, that doesn't make any sense because colors and numbers don't mix. What we're exploring here is basically how we've decided fundamental parts of math work, and what that means for all the other mathematical ideas we might encounter. Like we said back in episode 1, set theory gives us the language we need to talk about logical ideas clearly and build on them. When we have a group of things and certain rules for how those things fit together, like binary operations, we're developing what mathematicians call an algebraic structure. It's kind of like the world building authors use to establish how their settings work, like whether dragons exist or what the different social rules are. There's an entire field of mathematics dedicated to identifying and describing algebraic structures called abstract algebra. And it might seem kind of, well, abstract, but abstract algebra and figuring out the rules for how things are formed is helpful in all kinds of ways, from probability to storing data. Now, at this point, you might be wondering why we bothered to take the scenic route, and where the heck we're headed, and how binary operations and abstract algebra help Jeanette and Erica with the story of their fruit basket. Let's apply all the work we've done so far to sets in general, rather than just real numbers. The point of talking about binary operations and algebraic structures is to show that the rules we have for manipulating sets aren't just stuff we made up arbitrarily. In fact, they follow a lot of the groundwork that shows up all over math. Specifically, we call the rules for manipulating sets set operations, which are a type of binary operation that creates a new set from doing things with two other sets. When Jeanette and Erica looked into their cart, they saw a whole jumble of fruit: ripe mangoes, sweet rambutan, apples, aki, tangers, langsat, and a few lychee. We can also say that the collection of fruit in their grocery cart represents a universal set, or all the fruit they're going to use for their gift basket. But there are many sets and subsets within the world of our universal set that represent different themes and make this collection much more than just a fruit basket. For instance, some of the fruit in their cart are agricultural products from the islands their ancestors are from, Jamaica and the Philippines. So, Jeanette reorganizes their cart by putting the fruit from Jamaica on the left side and all the fruit from the Philippines on the right. She ends up with the tanger, mango, rambutan, and aki on the left, and on the right side she has lychee, rambutan, langsat, and more mango. Remember that in math, when we make a new collection using only things from another collection we already have, we call it a subset. So here we have two subsets. Let's call the subset with the fruit from Jamaica J, and the subset with the fruit from the Philippines P. But oh no! While they were focused on reorganizing their fruit, another cart accidentally runs into them, causing their fruit to get all mixed up again. So now set J and set P are merged together. In fact, just like smashing real numbers together is the binary operation of addition, merging two sets together is also a binary set operation, called the union of sets. Now we have the union of the subsets J and P, which has mangoes, rambutan, aki, tangers, langsat, and lychee. Of course, in math, we like to be a bit more precise than smash or merge. So the formal definition for a union in math lingo goes like this. For any two sets A and B, some element X is in the union of A and B if and only if X is in A or X is in B. Now, what the formal definition is trying to say is that if we have two sets named A and B, then any element that's in their union either came from A or B. It could be in A, it could be in B, it could be in both. We don't care. It just has to be in at least one of them. And just like adding or multiplying two real numbers gives us a new real number, putting two sets together also gives us a new set, because you're either in J or P or you're not. Fortunately, looking at the set J union P gives Erica some ideas on how they can tell a story about the significance of fruit for both of these island countries. Now that they've gotten their cart organized again, we can make a Venn diagram instead, which is a visualization that shows the relationship between sets. Mangoes and rambutan are cultivated in both Jamaica and the Philippines, so those two pieces of fruit live in what we call the intersection of J and P, which is the set of elements two sets have in common. Finding an intersection is another set operation. Formally in math lingo, we say that for any two sets A and B, some element X is in the intersection of A and B if and only if X is in A and X is in B. This means that for two sets A and B, the new intersecting set contains every element that's in both A and B at the same time. With such thoughtful choices that we get from looking at the unions and intersections of our sets, this fruit basket is going to be the basket of the century. In fact, Jeanette can already see how she'll tell the story about mangoes and rambutans sharing sweetness in homes. Except we can't forget about that apple that's still left in the grocery cart. The only apples usually grown in Jamaica or the Philippines are star apples, and this apple is certainly no star. So the apple is not an element of J, P, J union P, or the intersection of J and P. It's just been rolling around the cart aimlessly, minding its own business. Since the apple doesn't belong to any of the sets we've talked about in our universal set/grocery cart, we say it exists in the complement, which is the set that contains all the elements in the universal set that are not in a particular set. Specifically, the apple belongs to the complement of J union P, because apples aren't typically extensively cultivated in Jamaica or the Philippines. Finding the complement of a set is another set operation, and complements are often written using an accent mark to show their relationship with the set we're focused on. So if a set is called A and we want to label the complement of A, we can write it as A with an apostrophe and read it as A complement. Apples are in the complement of J union P, but we could find the complement of just the set P and find everything that can't be found and isn't grown in the Philippines. In our cart, that's tangers, aki, and apples. Or we could find the complement of the intersection of J and P. That's everything that isn't grown in both Jamaica and the Philippines, which in our cart are tangers, aki, lychee, langsats, and apples. So even within just one grocery cart, there were many stories to tell, and set operations can help us reveal and tell that structured story about how sets can relate to each other. No matter what kinds of sets we're dealing with, the structures and rules we develop within universal sets help us interpret and interact with the world around us. There are all types of sets in this big world that once we combine them with each other, we can find something interesting, like blending families together or making fruit baskets. Next time, we'll continue exploring the relationships between sets, set operations, and how they can help us make sense of the world when we take a deep dive into Venn diagrams. Thanks for watching Study Hall Real World College Math, which is produced by Arizona State University and the Crash Course team at Complexly. If you like this video, give us a like and subscribe. You can learn more about ASU in the videos produced by Crash Course and the links in the description. See you next time.